Angiphethe out yami pintshami skipan.
Hola my brother. Afede mina nguPhilip Hot bafethu mathebula ilikeleza nathi la ilishada.
Hayi ke lezi nathi impela la ilishada Mr Mathebula.
Sure.
Ukhulele phi bra?
Mina ngikhulele enhlake yethu Orange Farm Extension 2 yabo.
So vele nje la born and bred.
Born and bred.
Uzalwa nesinko my dog.
Yeah, sure.
Manje khamba kanjani ke ifundo zakho the same?
Hayi imfundo nozihamba kahle enhlake focus ikhona yabo. I last episode angisola. Angisabuyi ifede la.
Last episode, Baba, the season is clear. Manje, what's your question for our teacher in the studio?
Yeah, sure. My question is, how do I go about calculating a pH of a solution?
Well, thank you for that question, Philip. Let's quickly repeat it for our viewers at home. He asked us, how do I go about calculating the pH of a solution? Okay, now you have heard about the pH already in grade 8, which is a long time ago. But we are going to start off by first taking a look at the ionization of water. That's going to be our starting point today. Now, ionization basically means when something breaks up into its ions. And in this case, we're going to specifically look at water when we have two water molecules and they break up into its constituent ions. So let's quickly take a look at what will water break up into. When we have two water molecules, because we've talked about acids and bases last week, one of them will be donating a proton, which is my hydrogen ion, and that will then form for me the H3O+, which is the hydronium ion or the oxonium ion. Now, because when it's donated this hydrogen ion, there will be left then an hydroxyl ion. So this means these are my two ions into which water will actually break up into, and that's what we call the ionization of water. Now, in this case, we're going to bring in some of our chemical equilibrium as well. We'll notice that the equilibrium lies far to the left. Now, what that basically means is, if we go back to our reaction over here, that most of the particles would rather want to be in the water form. That means the H2O form. They don't like to break up into H3O+ and OH-. Okay, now from the H3O+ and the OH-, we can go and multiply the concentration of those two things to end up getting the ionization constant for water. And that's what we're going to be seeing as Kw. Now you'll notice Kw, we can go and find by saying the concentration of, remember that we use square brackets to indicate concentration, of the hydronium or the oxonium ion multiplied by the concentration of the hydroxyl ion, and that's then given as a specific value of 1 times 10 to the power of -14. Okay, so that's something that you will be given, where your Kw, which is your ionization constant of water, is equal to the concentration of the hydronium ion multiply the concentration of the hydroxyl ion, and that gives you 1 times 10 to the power of -14. Okay, so keep that in consideration. Let's go and take a look and break them down into the irrespective different types of concentrations. So first off, if I've got my Kw, and we said that these two multiply, giving me 1 times 10 to the power -14, then it means in pure water. Now, pure water means that there's only water molecules involved. It's not like your tap water where you've got chloride ions and magnesium ions and all those things. It's just water molecules that will be in that solution, and that would mean that those two concentrations of the hydronium and the hydroxyl ion will be the same. And if they are the same, then it means each one of them will be 1 times 10 to the power of -7 mole per cubic decimeters. Now, when we are going to take a look at an acidic solution, then it means that in this case, there's going to be more hydrogen ions. Now, when we talk about a hydrogen ion or a hydronium ion, it basically means for us the same thing. So that means in an acidic solution, which will release more of my hydrogen or hydronium ions, that means the concentration of those two, or that one specifically, will rather be higher than the 1 times 10 to the power of -7, which you can actually see. Now, if it's a basic solution, then we are going to take a look still at the hydronium ion concentration, but now it will be less than the 1 times 10 to the power of -7. Now, the reason how come I'm constantly going to refer to the hydronium ion concentration and not the hydroxyl ion concentration is because when we do our pH calculation, which I'll show you a bit later, we only use the hydronium ion concentration. We do not include the hydroxyl ion concentration in our calculation. Okay, so as we said, if it's a basic solution, then the hydronium ion concentration now will be less than 1 times 10 to the power of -7. Okay, now the pH of our solution, as you should know by now, that's an indication of my acidity or basicity of a solution, and the pH calculated by using the logarithm of the reciprocal of the hydrogen ion concentration. And that basically means, as I've said previously, whether we use hydrogen ion or the hydronium ion, it means for us the same thing. So here's my formulas that I can make use of either one of these two. We can have pH, each will be equal to the log with over 1 over the concentration of the hydronium ion, or you can say pH is equal to -log multiply the hydronium ion concentration. Okay, now you do know your pH ranging from grade 8, as I've already said, it's always between 0 and 14, and that means if it's 0 up till 7, it usually indicates for me an acidic solution, and if it's between 7 up till 14, it means it's a basic solution. And if we've got 7, then it means it's a neutral solution. Now do not forget, when we talk about an alkaline solution, it means it was a base that is soluble in water. Now, many a times you do find bases that's not soluble in water, then we just call them bases. But if they are soluble, then we call them alkalis. But they still got all the basic properties and things that we do need for bases. Okay, so let's quickly go on, and we're going to take a look at now how we can end up taking a look at my pH value then, depending on the concentration of the hydronium ions inside my solution. So once again, if it's a pure water, we said that these two concentrations are equal, and they will be 1 times 10 to the power negative 7, and that's how come we end up though with a pH of 7. If it's an acidic solution, where the hydronium ion concentration is greater than 1 times 10 to the power negative 7, then my pH will be less than 7. But if it's a basic solution, and this concentration is less than 1 times 10 to the power negative 7, then the pH will be greater than 7. Okay, now we're going to quickly take a look at an example of how to end up calculating the pH value of a specific acid. Now we're going to be taking a look at a mono, di, and triprotic acids. Now protic means the number of protons, and when we talk here about protons, we talk about hydrogen ions. Okay, so let's quickly take a look at what I've got for you as an example. We're going to have sulfuric acid, which is H2SO4, and it's going to be having a concentration of 0.2 moles per cubic decimeter, and we would need to go and calculate the pH of the solution. Now what's important about this concentration given is it goes for every one of these ions. That means if I'm taking a look at the sulfate ions and the hydrogen ions, each one of them will be 0.2 mole per cubic decimeters as a concentration. But now something that we've noticed in this case is my sulfuric acid, which is H2SO4, contains 2 of my hydronium ions. Okay, so that means what we're going to need to do with that 0.2 concentration is we'll need to end up multiplying that with 2 so that we end up then with what is the total specific concentration for my hydrogen ions, and that's in this case was going to give me then the 0.4. So if we take a look at it, because there's 2 of my hydrogen ions involved, we're going to multiply that with the concentration to end up giving 0.4, and whenever we call or have something that has got 2 hydrogen ions, we call it diprotic. Needless to say, if it had 3, we would have called it triprotic, etc. So all that we're going to do from there onwards, we're going to take that 0.4 and we're going to punch it back into my formula, and from there onwards we will be able to find our specific pH value. Now we're going to take a look at one more type of example that's a little bit different than what we've just done. Now let's take a look. It gives me here 60 cubic centimeters of 0.5 mole per cubic decimeter solution of a hydrochloric acid added to 0.8 grams of calcium carbonate powder. Now the calcium carbonate in this case is going to be dissolved completely. The first question asks us to write down the conjugate base of the hydrochloric acid in the reaction. Now, if you can remember from last week's lesson, conjugate means the partner of. So our bases always partners with an acid. So we need to go and figure out, okay, what was the acid? And then once it is losing, in this case, a proton or a hydrogen ion, it will then become the conjugate base. So if we take a look at our reaction, because we're talking about hydrochloric acid, it's going to be losing a hydrogen ion, and that's going to end up giving me, in this case, Cl minus, which is in this case then going to be my conjugate base. So remember though again that if I talk about a conjugate acid, then it came from the base. So it's always an acid base that partners up. Before the arrow we call them acids and bases. After the arrows we call them conjugate acids and bases.
Angren.
Angimnandi mfethu ubawa kabatshela bathi cha.
Mina ngurich kabaluya ngithola intwana eosam mfini.
Rich baloyi.
Sure.
Yo, mali nomuthi.
Hayi sibo.
Alright, Bishama, utshele kahle ke mina ngitshela belungu lapha base studio. What is your question?
My question is, which indicator should I use to indicate the endpoint of a titration?
Well, thank you, Rich, for your question. Let's quickly repeat it for our viewers at home. He asked us, how would I know which indicator to use to indicate the end point of a titration? Now, we have spoken about a little bit about titration calculations last week, and we said that's where we're going to see where our acids and our bases is going to neutralize each other out. Now, we will have, though, different types of neutralization points, so it won't always be a pH of 7. It depends on whether you're using strong or weak acids or bases. Okay, now also remember, though, that our indicator, they usually help us there to identify a color when this change has actually occurred. And we get obviously different types of indicators, and they've got different pH ranges ranges with which they are sensitive and which they will work in. Okay, so what we are going to take a look at is some of these color changes and obviously the indicator that will go with that. So the first thing that we're going to say here is that our indicators are used in titrations to indicate our end point. And we said that the change in our hydronium ion concentration will cause a shift in an equilibrium, which will cause the color change of this indicator. And the pH at which this color change takes place is the end point. So remember, the end point is where these two things is going to end up neutralizing each other. Okay, so let's quickly go and take a look at the different types of ones that we can get. So first off, if I'm going to use a strong acid and a strong base, then we end up finding, in this case, a pH of 7 as my end point. And this means we are going to be using our indicator, which is going to be bromothymol blue. Now, bromothymol blue is going to be yellow in an acid, and it's going to end up being blue in a base. Now, usually at its end point, it's kind of a green color, but you've got to be very careful, because if you add one drop more in, it's going to turn again to either an acid or a base, depending on what one you've got most of. Okay, now also something else that you need to take a careful look at is your graph of your pH ranges where this endpoint takes place. And you'll see that this graph is a little bit different than what you're used to. Typically, where the endpoint occurs, you're going to have a vertical point on your graph, and that's then where we will basically see the pH at which this endpoint occurs. Now, let's take a look at when I'm going to have a strong acid but a weak base. Now, if it means I've got a strong acid, remember it talks about ionizing completely, and that means that pH range will then fall a little bit more to the acidic side, which is then below 7. So, as you might have guessed, the pH will be below 7. The type of indicator we're going to be using is methyl orange in this case, and this is going to be a reddish color in an acid, and it's going to be a yellowish color in a base. And usually at its endpoint turning, it's a kind of an orange color. Once again, you've got to look very careful to see that color change taking place. Now, if we take a look at its specific endpoint graph, once again, wherever you find the vertical point of this graph, that's where the endpoint occurs. And as we said, this will be below 7 because it's more of an acidic solution, because we're using strong acids. Now, the next one that we're going to take a look at is when we talk about a weak acid and a strong base. Needless to say, let's quickly run through what you can expect from them. We're going to have a pH higher than 7. We'll be using phenolphthalein as my indicator. It's going to be colorless in an acid, and in a base it will be a nice bright pink color. And now my pH difference will be around about 9-ish, which will be higher than 7. Now, if I've got weak acids and bases, they do not have a very sensitive pH range. It was going to be around about 7, and we don't have an indicator that will actually indicate that.